Hello everyone. So this tutorial is about how to do a simple fluidized bed problem. So what we are going to do is we're going to use a Eulerian granular model uh, to uh, to simulate um, a fluidized bed problem, and this is going to be a Eulerian simulation. What do I mean by that is both uh, the fluid phase and the particle phase is going to be solved as a continuum phase. So it's similar to, you can say, VUF model, where two different phases are solved as a continuum phase. But in this case, one phase would be a solid particle. So there will be some other calculation come into the picture. For example, collision between particles, drag is also always there. So there are some other parameters comes into the picture. Okay, so let's get started. I will do a very simple 2D fluidized bed. 3D is the same thing. It's just adding another dimension. So mesh should be number of elements would be higher. Simulation will take longer, but other than that, it's the same thing. Okay, so I'm gonna do a 2D one. So I'm gonna create a XY sketch. Going to sketching, rectangle. Okay, I'm gonna make a small one. Zoom in. Dimension, I'm gonna select a bed of 1 meter height. Okay, and um, let's do 0.4 meter width. Okay, so 0.4, and the vertical height is 1 meter. Okay, we can select 1.2 as well, up to you. Okay, let's then let's say 1/3 of our bed would be filled with particles with a specific porosity, and we're gonna introduce a uniform flow from the bottom, trying to see how the particle bed will fluidize, or like bubble will form between the particle beds, how the fluid will pass through the particle bed. Okay, there are a huge number of applications for this kind of problem in chemical industry, in oil and gas. So you guys can take a look over there. All right, so surface from sketches. So from this sketch, geometry is pretty simple and straightforward. So I just have this surface, and let me make this one fluid. Okay, I think we are pretty much done. There are two ways to introduce the particle bed. One is you'll see in the Fluent using the a region to patch the particle in this surface. Other way would be if I can like uh, create a line and split the two surfaces. I can use one of the part as to patch my particle. I'll just go with the difficult one. I think everyone knows how to split the face by now, and like how to specify that region for particle. So I'll just show the other new method. All right, so I've generated it. Close this one. Let's do the mesh. About the mesh, the this is one of the most important thing in this kind of simulation, because a lot of them fails because of the mesh. You'll see, like when you start the simulation, it keeps diverging. It keeps diverging. Content integration will go off. So why is it happening? It's one of the reason is mesh. Other reason I'll explain as I go through the simulation, setting up the simulation. One core reason is the mesh, your mesh. It's not like, I know this is going to be a fluid flow as well, and as according to the physics of the problem, what we should have done was creating a finer mesh near the wall because of the no slip condition. And I'm gonna just use a structured mesh, so applying a phase meshing here, and element size. Um, I'm controlling this one because I want to have uniform elements in all over the domain. You can use the sizing as well, but I'm just directly using that. So let's see what will happen if I say 30 millimeter. So you want to have these kind of uniform elements in all over the domain because there will be particles, and the particles are going to be calculated based on the averaging techniques. And not only, so that's why not only at the edge, but everywhere you need to have a fine mesh. Okay. And a multi-phase problem like this with particles, I would recommend using uniform mesh all over the domain, even though you know that it's important for the fluid for at the edge, but use a uniform mesh all of the domain. It helps solving for the particle phase. Okay, so this is one recommendation. I think this should be good enough, but I would just in case increase it a little bit more. Okay, number of particles is pretty low, so I can go higher. Okay, this looks fine. Okay, you see I have uniform grids in all over the domain. Everything is 5 millimeter element size, square elements. All right, so inlet and outlets. Let's see. So the bottom surface would be my inlet. Again, Fluent is name sensitive, so if I name it inlet, it's gonna be set as a velocity inlet type of boundary condition. But again, you can change it in the Fluent, so don't worry about it. Inlet, outlet, and I'm just gonna drag over these two. These two would be my walls, side walls, okay, and the middle would be my fluid domain. I like to specify everything because this helps. Sometimes you can't find the domain you want or the surface you want in Fluent, and you have to create a new surface. That's a hectic job. So it's always good to specify everything. All right, so I have my inlet, my outlet, my two walls. See, this one is red as well, if you want to take a look. And this is my fluid domain. Okay, these two are walls. Okay, so I'm pretty much done with the mesh. I'm gonna update it. It's updated. So I'm gonna close and open up the Fluent. I'm gonna use a double position. I don't actually need much, but I'll just go with 4 processors, or maybe 8. Start like giving overestimating the number of cores actually slows down the simulation. So don't just go for a higher number. Depending on the number of elements you have, choose a suitable parallel cores that would actually give you the optimum performance when you're solving any simulation. All right, so let's check the mesh if I have any negative elements. No negative volume. This would be a transient case, and gravity is important. So 9.81. Otherwise, particle would just leave the domain with the flow. Okay, and let's go to the model. I'll just enable the energy equation. I'll just add both cases to show that both works. Viscous, I'll just stick with this one, with the default one. Multi-phase, this would be an inhomogeneous model, Eulerian model. There would be two phases. Use a implicit volume fraction formulation. Explicit, like the difference between these two is the way they are solving the equation. So implicit will will help you converge the Navier-Stokes in a better way. Okay, so use the implicit. Explicit will, if your boundary condition and everything is not in the within the proper region, it will keep diverging. So implicit will give you more range of, if you're new, it will give you a better range of solving the simulation. Okay, it will give you less headache in converging. Okay, click apply, and these things will pop up. Okay, okay, everything, some material methods have changed. Click OK. Go to phases. So I have primary phase. Before going over there, let's add the material for particles. Okay, so I have air as gas. I'm okay with that. I'll add one more particle. Let's just select any of the particles. Okay, you need to know what kind of uh, particle properties, like are you using a glass bead, are you using sand, so what is the density of that material. You need to know all of these. I'll just select some random numbers in here, but make sure you know your particle properties. So I'm creating this, I'm overwriting the water liquid with particle density, solid particle density, I would say maybe 2700. Specific heat and thermal conductivity, I honestly don't know. Other things are not that important. I'll not change anything else. Uh, Change in create. Yes. There you go. So let me check. Okay, particle density has been changed. Air is there, solid is not important in here because I don't have any thickness or anything like that, so solid is not being considered. And after that, let's go back to the multi-phase. So there you go, phases. So we were in the models, now we're in the phases. Primary phase, so primary phase would be the fluid. Okay, so air is material is fine, so I'll say this is my gas phase, and you can click apply or you can do both at the same time. So secondary phase would be my particle. Okay, and this is, let's say, particle. Okay, it's easier. Sometimes you will mess up phase 1 and phase 2, which one is phase 1 and which one is phase 2, so I don't want you to go over there. The diameter is here, but before that, select the granular, because we're going to consider a granular particle bed. Okay, this is not a packed bed, so I'll not select an packed bed option. We're going to do a fluidized bed problem. Diameter is constant, but you can use a variable range as well. So there are new input parameters and everything. So I'm going to use a constant diameter particle. So I'm going to have a particle, very small size particle. Let's say this is 300 micron or 0.3 millimeter size particles. Okay, very small particle. There are other models that can do simulation similar to fluidized bed. For example, you can use dense discrete phase model, this one. Okay, uh, but the problem with that one is you should use that for a very small size particle, and uh, the the clustering of particles should be less. So what I mean is the particle should be dispersed. Okay, so they use this kind of model for dust collector or cyclone separator. Those would be ideal for this kind of model. But for fluidized bed problem, this would be more suitable. Okay, for simulating this kind of simulation. All right, and for okay, I'll skip that. And the granular viscosity, I honestly don't know, so I'm gonna use Samuel O'Brien model. You can use GitHub as well. Or some other models. This is a pretty popular model. I don't know about these things, so I'm just gonna. This is important, packing limit. So this would limit packing. It means it is related to the porosity. So even if you compress your fluidized bed, this is the maximum packing it will do. So still there would be 0.47 voids. Okay. Uh, so the way they calculate the uh, for void fraction is which would be in this case 0.47, 1 minus 0.63. Void fraction is volume of void over the total volume. Okay, over the total volume. So this is the maximum packing limit it will go. So there will always be 0.47 percentage of voids. Okay, this will not compress more. This is the maximum packing limit. It can go less, but it cannot go more than this. Okay, and after that, particles. I think I set everything up in here. Gas doesn't have anything. Phase interaction, drag coefficient. There are different ways. For example, you can use this one. You can add modification. You can add the constant for the drag coefficient. You can play, like if you have information, it can make it easier for you. Let me apply first. I think some of the parameters didn't come. Let me check. Secondary phase is okay. I forgot to change. What happened? I should have clicked apply. I changed back, so that's why I don't see the other options over there. Okay, let me change it back. 0.0003, 300 micron, granular viscosity, Sam O'Brien, 0.63, everything the metal. Click apply. Primary phase, this is gas. Yeah, I guess you have to press apply every time you make any changes in any of the pages. Otherwise, as you can see, it doesn't update. That's weird, but anyways, I didn't notice it before because I clicked apply every time. But anyways, click apply every time you make changes in any of the pages before going to the other one. All right, so when you come to the phase interaction, gas particle, you can select what kind of drag model you want to use. Particle is different. It's gonna ask you the restitution coefficient. This is related to the collision model. Okay, like how much due to the collision, how much it should push back the other particle. Okay, and this is directly related to that. You can get this from experiment, from simulation. Usually the experiment they do is they drop one particle and see how much it bounce back higher. Okay, and then they get the ratio of the dropping height and the jumping height, and that's what this restitution coefficient is. You can take a look for more details. So gas particle, there you go. You see I have more options now. So I'd recommend you can use GitHub, you can use Sam O'Brien. Okay, so that solves the problem. But if you know your minimum fluidization velocity, and then you can actually refine your drag coefficient, drag model better in a better way. So Sam O'Brien para model has so you can specify the void fraction. In our case, it is maximum was 0.47, but it can go lower. I think higher. It should go higher. And if you know the minimum fluidization velocity, what this will do is this will modify the model, modify the constants in the model, and it will generate the drag coefficient in a different way, which they are proposing that it would be a better drag model for your case if you have those information. But if you don't have those information, just select Sam-O'Brien. This works well as well. Okay, and there are other options. The lift coefficient or virtual mass coefficient is, for example, when a particle is moving, we are actually neglecting here due to the particle motion, the uh, drag affecting the fluid due to the particle motion. We're actually ignoring that because it would increase the computational time by a big margin. Okay, but if it is important in your case, for example, you have large particles and small number of particles, and that is very important. Maybe in your case that actually affects the full bed you're analyzing, then enable this one, surface tension coefficient, and so on and so forth. See which parameters are important in your case. We're just going to do a simple fluidized bed. And interfacial area, let's go with the default ones. I'll not change anything in here by adding more to it. I think I pressed apply, right? Samuel O'Brien. Okay, click apply, close. Okay, so I have particle and air, and then we are done with the models. We're done with the materials. Let's go to cells and condition. Let's go to operating condition. I'm just going to go with the default atmospheric pressure, atmospheric temperature. But if you need to change anything over there, do it over there. This is fluid. I don't actually have anything to change in here. It's not like the bed is porous or anything. And after that, boundary condition, inlet. So this is mixture is selected. So I'll go to gas inlet. So fluid is going to be coming in through this inlet. So I'll say magnitude normal to boundary, so that would be like this direction from bottom to top. Magnitude magnitude is, let's say, 0.3 meter per second. Okay, I'm just selecting something that should be good. Temperature, it's fine. 300 is fine. I just want to check something. Okay, looks good. And boundary condition, inlet, let's go check the particle inlet, because I don't want to inject more particle in it, just the fluid. So if you go to multiphase, the volume fraction at the inlet coming in is 0, so there would be no particle injection, only fluid injection. So keep it as it is. Velocity magnitude is 0 as well. There is no particle coming in, the temperature and everything. All right, at outlet, this is a pressure outlet. So one thing you want to have is sometimes due to the fluid flow, the particle will go up. And if it is a small particle like ours, the particle is you'll see some of the particle will try to leave the domain if you are injecting at a high velocity. So how to like in some cases we don't want our particle to leave the domain. So if you want to do something like that, backflow for this particle pressure outlet, and just say backflow volume fraction is 1, so particle will just bounce back and drop back. Okay, but if you don't want to interfere with it, just keep it as 0. Okay, so this will only bounce back the particle, not the fluid. Fluid will still leave the domain. Okay, click OK, and gas is fine, I think. Let me check. Okay, walls, so let's add some temperature at the walls to see the temperature difference. Specified here, what happened? Oh, okay. I'm selecting the gas phase. So select the mixture and thermal temperature. Let's say 350, for example. Let's say 330. Okay, click OK. I think we're done on here. I'll just go with default everything, methods. There's couple simple, couple, well, both are fine. You can use the higher order one. I'll just skip that. And monitor, I'll just go with this one. You can do hybrid initialization. You can use standard initialization. I'll just go with standard, and then I have to patch. So let me show you what is happening in here. So if I go to contour, phases, and interior fluid domain, you can deselect everything. Mixture, particles, volume fraction, save and display. So as you can see, there is no particle in here. Everything is 0. Okay, because when I initialized, uh, it has been initialized with a primary phase, which was gas, and I didn't specify where should the particle be. So what I can do is I can patch, after initializing, I can patch the fluid, the particle. So what I can do right now, either we could have done in the geometry by splitting the face and creating a surface. We would have said, well, this surface should be particle with this porosity. But if you haven't done that, then we can always go to adapt, sol register, new region. So we're going to do a region adaptation. Quad shape is fine because of our shape. It's going to be inside, and there will be 2 coordinates. So you can consider this one as a rectangle corner point. So this point and this point. Okay. So x minimum, y minimum is 0, 0, because we started our geometry from the origin. So 0, 0 is fine. X max, y max, which is this point, would be, let's say, you can go beyond, but don't go lower. So uh, our width was 0.4, right? So 0.4, and y max is let's say this is 0.4 as well. Okay, save and display. So you can see this is the domain region we have selected. You can play around it to take a look. Let's say 0.2, so this would be like this. 0.4, this is like this. Okay, I think I created 3, but anyways, then close, click OK. So we have already initialized it. Now it's time to patch. So I'm going to patch particle, volume fraction. I don't actually need these two. I think this helps with the patching, but anyways, I'll just leave it as it was. Okay, volume fraction. So how much particle should there be? How much percentage? Let's say the particle over there is 0.6. Okay, a little bit lower than the maximum packing limit. And fluid domain, I want to patch it in the region I have selected. Click patch. Okay, something changed. So let's see if it was done properly or not. So volume fraction of particles, and as you can see, 0.6 volume fraction of the particle is in this region. Rest of them is 0. Okay, so it was initialized properly. If you want to monitor it, let's see, I'll add one solution animation. So this solution animation option will come only after you have already initialized it. So make sure you have initialized it. Otherwise, you will not see the solution animation in the calculation activities. Contour 1, I'll just preview. So this is the this is going to be shown in window 3. Record after every time step. No, let's say record after every 50 time step. Okay. Let's make it lighter. Click OK. So there is one animation created over here. Let's go to run calculation. Time step size, I'm going to select 0.001. Number of time steps, let's do 0.3 second, okay? So 300. And so there are some options like fixed, adaptive. So current number is very, very important. That is a non-dimensional number. So current number is directly, what is current number? You can check in the web or in the ANSYS help option as well. The way it is, that is actually directly related to the element size, the velocity you're introducing, inlet velocity, and as well as not only the inlet velocity, the velocity all over the domain, and as well as uh, I think those two are mesh and the velocity that directly relates to the Reynolds number. I think, as well as the time step size. Okay, so this has a proportional and inversely proportional relationship. So the way it works is if you have a higher velocity, current number will go high, and you don't want that because that would cause divergence. Okay. Other way is if you go lower time step, current number would go low. So that's actually beneficial. But if you go to a lower time step, for example, if I say 0.0001, okay, that would take a longer amount of computational time to just do 3 second or 0.3 second simulation. So you don't want to go over there. But again, if you go to a small, like a larger time step like this, current number would go really high. And actually the threshold is you don't want your current number to go above 1 or 2. You can calculate the current number, and it actually shows the current number in the console as well. You can check after time step ends, it shows the current number, a calculated current number. And other than that, the mesh element is, so the larger your mesh element is, your current number would be lower. Okay, but the problem with that is if your element is very large, you lose the calculation influence, like how your accuracy will go really, really down. Okay, so these are all like double-edged swords. So you need to find a balance in between all of them that actually will give you an accurate but faster solution. Okay, so let's do calculate and see. One other thing I want to mention is if it diverges initially when you start the simulation, if it diverges really fast, so the black one is continuity, if the continuity diverges really, really fast, in your case, one thing you can do is you can refine the mesh more, or uh, actually I would recommend before doing that, introduce your velocity really slowly. So the way I introduce the velocity is right from the very beginning, introduce the velocity inlet, velocity of the fluid from 0 to directly 0.3, I think I specified. Okay, so I'm jumping the velocity by a good margin. That actually causes instability, and this kind of simulation sometimes can take it. So I would recommend introduce your velocity increment very slowly, very smoothly. So let's say 0.03 meter per second at the very beginning, and then when it maybe 0.1 second passed, then introduce 0.6 or 0.2 second, then 0.3 seconds, so on and so forth. This will make your simulation more stable. Okay. All right, so let's come back after we have finished the simulation. As you can see. All right, so we're done with the simulation. I added 200 more time steps to do half-second simulation. So this is the coordinate number I was talking about, the CFL number. And as you can see, it is directly proportional to the velocity and time step size, or inversely with the grid size. Okay. And you want to maintain it, the best would be below 1, but again it can try to be at least in the margin of 2, not go beyond that. Okay. All right, so let's take a look. So this is the final volume fraction contour, and let's see how the animation looks like. Go to the playback. Let's do a slow, because I have very small number of saved contour plots. I'll just go really slow. Increment. Okay, play. So this is how it's changing. Okay, and as you can see, the particle bed is rising, the bed height is increasing. It's going to fluidize, but I have a very small time simulation, half second, so it's not good enough to show all the big bubbles and everything. But anyways, you can run it longer to see what will happen. At the top, these things you're seeing, I think this happened because I applied a backflow condition for the particles. So what is happening, some fluid is taking some of the particles near the outlet, and sometimes what happens is it gets stuck instead of bouncing and dropping back. It can happen due to the fluid flow is like pushing that very small particles near the outlet. Other times, even if when I reduce the velocity, it was still stuck in a small layer. So I'm not very sure about that, but usually it should not happen. Sometimes it happens. So just rerun that. In that case, so this is the volume fraction at 1. So let's see if you can get a better look at the volume fraction. Instead of auto range, let's say minimum is 0, maximum is 0.6. Let's take a look. So, oops, disappeared. 0.63 maybe. There you go. So this is the maximum packing is happening in here due to pushing of the fluid. More void has been created at the bottom. So there are so on and so forth. You can take a look at a lot of stuff, how the fluid is passing through here. So you can check the gas volume fraction, the gas velocity. I should go for outer range. Okay, so this is how the gas is passing through here. You can check the velocity of the gas phase. Okay, velocity of the gas phase, velocity of the particle phase. Okay. Anyways, so this is how you can set up a fluidized bed case. One last thing I want to show you is, instead, like if you are very concerned about and not know how to set up the control the current number, it's not working, you can use an adaptive method as well. So what it does is uh, it it asks you, I think, multi-phase. I haven't done this for a while, so let's see. Duration specification method, increment time. So I think it increases the time step slowly. Uh, there was an option for the CFL condition. I don't know. I used that in the older version. I guess they removed it. Okay, global current number. Okay. So what you can do is you can specify the current number. So if you like, this would be fixed in every time step. It will renew the global core number. It will maintain the global core number. By how? By changing the time step size. Okay. So your time step size would not be constant. Like in my case, I use 0.001, but the time step size will change, and to maintain the current number at 2, let's say. Okay, so this is one method uh, to stabilize the simulation, but the problem you might see is your time step size. If your other boundary condition is not suitable, like it's extreme, then what will happen is your time step size will go very small, and it would take an endless time to run the simulation, complete the simulation. So again, I would not recommend that, but if it's not working and if you just want to see if it works or stabilize the simulation at the very beginning, you can use this method as well. All right, so this would be it. Hopefully, this will help everyone. Thank you.